Hello, and welcome to Answer Everywhere. This is a live show where every episode we take a look at an unfamiliar code base and kind of poke around, see what's happening. Today we're looking at ANTLR, the parser generator that's written in Java, and it targets a bunch of great languages. This was a fan request that I got, and I wanted to do this today instead of as part of fan request roulette, just to make sure that we get to it. And the requester doesn't wait too long. Also, there are a couple of announcements that I want to make, things that are a little bit different this week and the next few weeks. One is that I'm having visitors coming this week, and they're going to stay about 4 weeks. The way that my office is set up, my house is set up, is that my office is you have to walk through my office to get to the in-law suite. So whenever I have folks stay here, it's a little bit harder to make sure that I am able to stream on my schedule because I don't want to impose too much on my guests. That said, I'll be around. I will probably do some code streaming, and not this week. I won't be able to do fan request roulette this week, but the remaining weeks I should be able to. And then, so what I'll be doing when I can't do the normal schedule this week is there's a bunch of things that I've promised to do, like videos to improve the sound on, or shorter videos created from snippets of other videos. So I'll try to work some of that in the next few weeks and get those up. There's also a video of me and my brother playing a game that I never posted, and I'll probably end up posting that in the next few days or the next week or so. And finally, somebody had asked me a couple of people have asked me about social media, and in particular, one person asked me if I had a Discord server. So I went ahead and created a Discord server. I'll post that in the show notes, and I'll also be more active starting this week on places like Twitter and Mastodon, and I guess mainly those things. So I'll post those handles in the show notes as well, and then join the Discord server. It will be cool. I don't know. I've never really used Discord, but I'll check it out. It seems to be where people like to hang out. So let's jump into ANTLR. I'm going to try to keep this relatively short, which I think should be feasible. In the context of this show, if you've seen other episodes, we should be able to have a sense of what's going on with ANTLR. We've seen a bunch of compilers. And as part of those compilers, we've seen things that do parsing, that create a grammar and use that grammar to parse or create an abstract syntax tree, all of that sort of stuff. So I'm expecting ANTLR to be more or less the same. I think the thing that makes ANTLR useful is probably some combination of speed and usability features and the ecosystem around parsing particular languages. So we'll try to see if we can see some of that. And yeah, so ANTLR is Java. Somewhere it should say Java. 26%. Wow. Wait, hang on. Java and Python. I'm guessing maybe Python's mostly for tests. There's also some C++, some C#, Go, and Swift. I don't know if these other languages are to support these target languages, but I guess we'll try to figure that out. But I'm actually surprised that there's really only about a quarter of it is Java. So let's take a look. So there's things like scripts in tool test suite. I guess let's take a quick look at tool test suite, just to see if we can figure out if this is where some of the things like Python are. We see mostly Java in here. Lots of tests. That's very good. Here's scripts. we have some Python in the scripts, like deploy to website, parse extended pictograph. I'm not sure what a pictograph is. Okay. And then as far as where the actual code is, my main guesses are either runtime or tool. And maybe there's code in both of these. So runtime has folders for a bunch of languages. So C#, C++, Dart, Go/ANTLR, Java, JavaScript, Python 2, Python 3, and Swift. So these maybe are the targets. I don't know if you would call these like the front ends or plugins or something. Let's look at, just for fun, let's look at Dart, just to pick an example. And in Dart, we have lib and test source util. And yeah, okay, so we have Dart files in the Dart folder, which would explain the presence of Dart here. And so we've got this library ANTLR4, and we're exporting a bunch of stuff. And then in here, we somehow have a bunch of parsey things. Now, I don't know if this imports any of the Java stuff. We're defining a bunch of stuff. This is what, token.dart. And we've got classes, like writable token. Yeah, we'll have to figure out how this stuff communicates with the Java, unless it's just a bunch of independent projects. But let's look at tool. Or maybe the tool creates like a kind of file that's consumed by the other stuff. I don't know. It's fine. So in tool we have we go to source ANTLR v4, which is a sign that this is probably Java given the folder structure, and we have tool.java. That's another sign that we're in Java world. And then we have Unicode, which I'll ignore, tool, again, semantics, parse, miscellaneous, GUI, code gen, automata, and analysis. Now, the most interesting to me that just kind of pique my interest are maybe automata and analysis, and possibly code gen. But I think the most important things are parse and semantics. So let's take a look at parse and semantics. So we have ANTLR lexer.g. I don't know what .g is, but maybe like a grammar file. And we have ANTLR parser and ANTLR builder. We have action splitter, which sounds like it's kind of like a helper function thing. Block set transformer action splitter listener. I guess you can listen to action split events. A grammar AST adopter. I don't know what it means to adopt an AST. This grammar AST, so S would be syntax. Okay. So grammar token, grammar tree visitor, left recursive rule walker. So I believe that ANTLR is a left whatever LL parser, and then resync to end of rule block scope parser, token vocab parser, tool ANTLR lexer, and v4 parser exception. Okay, what is this? This is parse. Let's pop parse out. Let's look at semantics. We have an action sniffer, in case you want to sniff some actions. Attribute checks, basic semantic checks. So these are checks. We have a rule collector, which kind of sounds like maybe some sort of container, essentially, with some methods. A semantic pipeline, more checks, in this case, symbol checks, a symbol collector, and a use-def analyzer. I'm guessing these might be important. Maybe I'll pop this out just so I don't lose track of it as I'm closing things down. And then what else do we have? So code gen and automata, and it might be the case that tool is like super important. So in tool we have ANTLR message, ANTLR tool listener alternative AST. What's an AST? Block action not AST, rule ref set AST. Okay. And then we have things like grammar interpreters, left recursive rule lexer grammar. So I'm not really sure yet how this is I don't have a good sense of the architecture. Let's look at ANTLR message. So ANTLR message, we're just going to import runtime token and whatever string template is. And we've got things like error and a grammar G, an offending token, and then an ANTLR message with an error type. But I'm curious, like, what do we do with this message? Do we send it somewhere? Get message template, toString, error type equals, get clause, message st. What is st? Get message template. Okay, I don't know. Let's see. I'm not sure what's going on with message. And in CodeGen, we have things like a model, target, action translator, Lexer factory, output model factory, source gen triggers, etc. Then for targets, we have the different targets like Python 2, Python 3, PHP, Go, Dart, CPP, etc. Okay, did I put CodeGen in its own little window? Okay, let's put that in a window. In Automata, you have an Automata ATN, automaton optimizer, an Lexer ATM factory, a range border characteristics. So I'm wondering if this is if the automata stuff is for like regular expression automata. We have ATM optimizer, author, Sam Harwell. We can optimize, which takes a grammar and an ATN, presumably automaton, and we optimize sets with G and ATN and optimize states. Optimize sets is going to take a grammar and an automaton. It'll check if it's a parser, in which case it says parser CodeGen doesn't currently support set transition, and we'll return. And then we'll get set removed states to 0. And we have this decisions function. And if character is lowercase, parser CodeGen doesn't support set transition. Then we do nothing, I guess. We continue. Where's decision? Decision state, decisions. So somehow we have a list of decisions, which we got from the ATN. Decision to state. And then we're going to look at some rules. Yeah, okay. I'm not sure. We call optimized states. What I'm not, we've got some commented out code for printf debugging. That's funny. I'm not sure still how this is organized. Like I don't know what the right entry point is. So maybe we can look at the GUI. We've got a basic font metrics, graphics support interpreter.java, test rig, tree viewer, and trees. I think this is for like visualization. What shall we do? Well, one thing we can do is we can see if we can find a main function. We'd already have Emacs open. Whoops. Should I just find grep main? We have static void main in C#. We have some main in Swift. We have test.cs main. Huh. What about lowercase main? DFA strategy. See if we can improve this search. Got a void main in Dart, but that's just for tests. Got some DFA stuff in Java. In your main startup code. So is this, maybe it's just supposed to be used as a library. Let's ask the internet. No, let's ask the AI. Try ChatGPT. in ANTLR 4, where is the coolest code? You know, the code that will make me look cool on the internet if I understand it. Okay, let me give you a taste of what it's going to give me a taste of. Use a code snippet that demonstrates the grammar and parser rules in ANTLR 4. There's going to be some grammar arithmetic. Start expression in a file. Expression has, I guess, parentheses and then an expression inside, which is a nested expression. Or maybe the star of two expressions, which is multiplication and division, etc. And then a number is one of these things. And a WS, I guess white space is, if you encounter white space, skip it. You see one of these, I guess this is essentially a regular expression. It's going to match as a number. And then you might be one of these operations. In this example, we defined a grammar called arithmetic that specifies the structure of arithmetic expressions. The start rule represents the entry point of the grammar. The expression rule defines various types of expressions, including nested expressions within parentheses, multiplication, division, addition, subtraction, and simple number expressions. The number rule matches numeric values, and the WS rule skips whitespace characters. Yeah, okay, that's fine and all, but that doesn't tell me where the coolest code is. Let's see what Bard tells me. And while we're waiting for Bard, I will ask, I don't want to regenerate a new response. Just do a new chat. So in ANTLR 4, what is the workflow for creating a C++ parser, let's say? So Bard is telling me the coolest code in ANTLR 4 is the code that allows you to generate code from your grammar. This is a powerful feature that can be used to create all sorts of interesting things. To use this feature, you write a grammar. It's basically telling me the same thing. Okay. So here's ChatGPT is trying to tell me about the workflow for creating a C++ parser. So we're going to install ANTLR 4. Define your grammar. Okay. The G4 extensions. So yeah, okay. So we are defining grammar as like a separate file. We'll specify the C++ target. In your grammar file, specify the target as C++. Add the following to the beginning of your grammar file. Grammar my language options. Language equals C++. Define Lexer rules. Define Lexer rules to tokenize the input source code into individual tokens. Lexer rules define the lexical structure of your language, such as keywords, identifiers, operators, and literals. Okay. Define parser rules. Define parser rules to define the syntax and structure of your language. Parser rules combine tokens produced by the Lexer rules to create meaningful language constructs. Okay. And generate the Lexer and parser. Using the ANTLR 4 tool to generate the Lexer and parser classes in C++. In C++, this is kind of my question. Run the following command in the terminal or command prompt. So this is going to, I guess, generate C++ from my language, from my grammar. And why does it say Arduino? It's just copying something from the internet in SQL. Or maybe it's just trying to recognize the language from the snippet. Is that what's going on? Maybe this is not a ChatGPT error. Maybe this is like a ChatGPT front-end error that thinks that, ChatGPT created this thing and some front-end, I guess, is trying to decide that that's SQL. And then, wait, where are we? Okay, so include the files in the C++ project and instantiate the Lexer and parser in your C++ code. So you're going to include Lexer and parser, and then you're going to get this ANTLR input stream input your source code. My language Lexer input, and then a common token string. And we're going to call tokens on Lexer. And so the source code goes into the Lexer object, and the Lexer object goes into the tokens object, or rather the function. And then the parser is going to take the tokens which by extension has access to the lexers and the source code to create a parser. And then we're going to parse the input in C++. And so I'm going to guess it's similar in Dart and Java. And so this kind of clarifies a few things. One is, what are the other languages doing? Well, they seem to be doing this stuff. It's basically like libraries to take whatever ANTLR, the like command line utility here generated. Oh, it's going to generate code, right? Generate the lexer and parser classes in C++. Yeah, okay. So it's going to generate code. And that code is going to be code that the structure of the code is going to be from essentially from the G4 file. And then we import the code in the target language. And so I don't know if the code generation is in Java or C++. So let's ask. In the language in the ANTLR code base, how do you spell this? ANTLR code base. There is some code that generates the C++ lexer and parser, correct? Is this code generation, this generation code written in Java or C++? Okay, the code, so according to ChatGPT at least, the code that generates the C++ lexer and parser in the ANTLR code base is written in Java. ANTLR is primarily implemented in Java, and the code generation functionality is part of the ANTLR tool. When you use the ANTLR tool to generate lexer and parser classes for specific target languages, such as C++, the tool reads the grammar file, typically written in ANTLR's grammar syntax, and generates the corresponding lexer and parser. Okay, so where's the about 11%? So okay, so let's ask the ANTLR code repository is about 11% C++ code. What is the C++ code doing in ANTLR? I feel like ChatGPT, you might be contradicting yourself. So, ChatGPT is saying the targets. So the C++ code in ANTLR does target-specific code generation. The C++ code in the ANTLR code base is responsible for generating lexer and parser classes specific to the C++ target. The code handles the translation of the grammar definition, into C++ code. And then lexer and parser runtime. The C++ code in ANTLR includes the runtime library for the C++ target. I guess that's what's in runtime, which provides the necessary infrastructure for lexing, parsing, and analyzing the source code. Okay. This includes classes and functions for handling token streams, parse trees, and traversal mechanisms. Okay, that's what I thought from its original answer. The lexer and parser classes generated by ANTLR depend on this runtime language for their functionality. Okay, so they're going to import some stuff, some C++ stuff, and that C++ stuff is in the ANTLR code base under runtime, is how I'm going to interpret this. The AST handling. The C++ code in ANTLR includes classes and utilities for creating, traversing, and modifying ASTs. I think this is basically the same stuff, essentially. And then visitor and listener interfaces. Visitor and listener interfaces that allow users to define custom actions to be performed during the parsing process. The C++ code in ANTLR includes interfaces and base classes for visitors and listeners, which users, I think this is essentially the same thing. This is all part of runtime, right? And the utility functions and data structures. Okay. So I'll just ask, would those considered part of the C++ runtime support? Yes, all the components and functionalities I mentioned earlier, such as target-specific code generation, blah, 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 can be considered part of the C++ runtime support. Okay, thanks, ChatGPT. All right, so I'm going to assume that ChatGPT is not hallucinating too much there, and that really that is what's going on in runtime, which is interesting. But probably the most interesting thing is actually um, the Java, and so I will proceed with that hypothesis and just kind of ignore the runtime stuff in the interest of time. So, but at least now I have a better idea of like what the workflow is. So we'll ignore runtime. Here's ANTLR v4. This is the main thing I opened. We'll get rid of these like auxiliary windows. And you know what? I should ask ChatGPT what the automata directory does. So ANTLR has a directory called automata. What does the automata code do? It contains codes related to finite automata, which are fundamental data structures used in Alexing and parsing. You have Lexer state machines. ANTLR's Lexer uses finite automata, specifically the deterministic finite automata or DFAs, to perform tokenization. So this is, we've run into deterministic finite automata or DFAs a few times before. First time we ran into them was in the source code to SED. The GNU project uses deterministic finite automata to implement regular expressions. So I'm just going to assume that this is just regular expression support instead of using their own, using a standard regular expression language. And we saw, I think in a Russ Cox blog post, he mentioned that DFAs were faster than most standard regular expression libraries. And so this might be one of the reasons that people like ANTLR. Okay, that being said, I think we're mostly going to ignore that for now, unless we have lots of time left over. Okay, so I guess we might as well start in roughly in order. What else do we have here? So automata, I'll get rid of automata. Sorry, automata. I thought I had like a Lexer open. So we have code gen. I guess let's go ahead and combine these. Windows, can I do that? Oh, this is the chats. I don't need that one. And let's go back and open this directory and find. Oh, okay, there is no Lexer. There's just ANTLR. Sorry, where's parse? Parse, okay. In CodeGen, maybe analysis. Wait, what was in tool? I think tool is really important. And then what was in analysis again? Analysis, pipeline left, recursive stuff, rule transformer. Okay. Let's look in tool. And then we also have tool.java. In tool, we have an AST directory, which we looked in before, which has got things like action AST, not AST, pred AST, rule AST, set AST, and terminal AST. And I think I want to keep this relatively short, so I'm not going to be able to look closely at all of this, but we can at least get a feel for how things are laid out. So let's look at rule. Let's look at Lexer grammar and left recursive rule. Grammar, semantics, message, grammar, transform, pipeline. Let's look at grammar. Default tool listener, I guess we can ignore. Dot generator. This might be the dot file, like what's it called? Graphiz. See if we can find graphiz. Dot part of graphiz generation aspect. Okay, it'll generate a graphiz file. Okay, and then we've got attribute and attribute resolver. Look at that. Let's look at attribute. That might be important. And then we have a grammar AST visitor. and action AST. Quantifier. Let's look at a few of these ASTs. Why not? And then that'll be enough for tool, I think. And I guess let's look at one of these G files before we go too far. You get a big note about the BSD thing, BSD license. This is the definitive lexigrammar for parsing ANTLR v3.xx grammars. All other grammars are derived from this grammar via source code control integration, per force, or by the gdiff tool. This grammar and associated grammars, a3parser.g and a3walker.g, exhibit the following traits, which are recommended for all production quality grammars. So this is some grammar, but for v3, and we're in v4, but I guess they still use this as the beginning. You have action structure, actions, argument specs, some stuff about fragments, arg or car set. I still don't know what this file type is. Obviously G is for grammar, but is this a G file extension? What is the G file format? Binary geometry files? No. G4. File with a G4 extension contains the grammar for a parser called ANTLR4. The ANTLR4 runtime is required to recognize the G4 file. After installation, the parser tool recognize the G4 file content as a language which needed to be translated into typical language. Okay. I guess G is just the ANTLR's grammar. I thought we had seen it before as another kind of grammar, but maybe either I'm mistaken or maybe that was an ANTLR grammar. I don't really know. So I'm going to just guess that G is custom to the ANTLR project. Let's see, grammar file. Comparison of parser generators. So Wikipedia has this comparison of parser generators, and everything seems to use DFAs. Yeah, including Alex, which is written in Haskell. And let's see, where is ANTLR on here? Is ANTLR not on here? Okay, so deterministic context-free languages is down here. And then what is this? Regular languages. Okay. We match by a sequence of replacement rules, each of which is essentially maps each non-terminal element to a sequence of terminal elements and or other non-terminal elements. Grammars of this type can match anything that can be matched by a regular grammar, and furthermore can handle the concept of recursive nesting. Every A is eventually followed by a B, such as the question of whether a given string contains correctly nested parentheses. The rules in context-free grammars are purely local, however, and therefore cannot handle questions that require non-local analysis, such as does a declaration exist for every variable that is used in this function? All right. The deterministic context-free language parser generators, I guess, or AGL, ANTLR, which has adaptive LL star, as opposed to ANTLR 3, which has non-adaptive LL star. And they're using, so B and F should be Backus-Naur form. I don't know what the E is. Oh, we get a pop, extended Backus-Naur form. A family of meta-syntax notations, any of which can be used to express context-free grammar. Okay, and then we have a bunch of other stuff that I haven't heard of. I've heard of Bison. Input grammar notation. So Bison uses YAC as the input grammar notation. And it does a bunch of different kinds of parsers, including LALR, LR, IELR, and GLR. And what else? I don't think I've really seen any of these other ones. Okay, so this is just back as now form. I mean, extended back as now form. Okay, so my original question was like, what is the .g file? But that doesn't seem to be answered here. Okay. They just close it. Yeah, right. All right, so let's look at, so this is the grammar thing. Let's look at what other grammars we have here. We have ANTLR parser. So this is the lexer.g, parser.g, ATN builder. I guess automaton builder. Let's look at automaton builder, I guess. Let's open all of these at the end. Action splitter, I'll ignore. Grammar tree visitor, grammar token.java. Scope parser. Let's look at scope parser. Token vocab, tool, ANTLR, lexer. Oh, I guess ant and ANTLR. No, I was going to say it was stands for a pun on automaton, ATN, the ATN abbreviation, but maybe maybe that was the original idea, and they used they swapped up the letters instead. Okay, all right. And then in code gen, we have things like lexer factory, parser factory, source gen triggers target, code gen pipeline. We have things like factories, parser, walkers, and then I guess the target is where the real rules are. So let's look at the Python 3 target just for fun. And that's, I guess, all we'll look at in code gen. And then now we're looking at actual source code. So here's rule.java. And how big is it? About 300 lines of code. The code looks very clean. What's that? All right. The rule is going to implement attribute resolver. And I'm able to click defined in attribute resolver. Let's look at attribute resolver does. So it's just some interface that has resolves to listable, resolves to label, whether things resolve to attribute dictionaries, to tokens, to attribute. Grammars, rules, and alternatives all have symbols visible to actions. To evaluate attribute expressions, ask action for its resolver. Then ask resolver to look up the various symbols. Depending on the context, some symbols are available and at some aren't. Alternative level. I don't know what all this stuff is, but let's go back to rule. So we're going to implement this attribute resolver thing. And we have a comment. Rule refs have a predefined set of attributes, as well as the return values and args. These must be consistent with action translator rule prop to model map. We've got some attribute dict, and we're going to add, so the attributes they have are like parser, text, start, stop, and context. And then we've got this valid lexer commands. I guess we have commands that we can send to the lexer. And this is just a hash set, which is just a set, right, in Java, implemented under the hood as a essentially probably a hash something or other, maybe a hash map. Anyway, our valid calls are mode. I guess the lexer can have modes. Push mode, type, and channel. Push mode, maybe push mode onto the stack. And then actions, we can pop mode, skip, and more. Then we have things like a name, modifiers, which is a list of grammar ASTs, rule AST, public rule AST. So the rule has some rule abstract syntax tree thing. Let's see, args, return values, locals. In which grammar does this rule live? So we've got some pointer to the grammar that we're a part of. If we're in a lexer grammar, we might be in a mode. Okay, so we can record what mode we're in. Whether we're case insensitive, named actions. Map a name to an action for this rule, like at init. The code generator will use this to fill holes in the rule template. I track the AST node for the action in case I need the line number for errors. All right. Then we can track exception handlers, and we have a list of action ASTs. Track all executable actions other than named actions, like init and catch finally, not in an alt. Also tracks predicates, rewrite actions. We need to examine these actions before code generation so that we can detect refs to rule, attribute, etc. All right, I don't really know what that means, but we've got some actions. Some actions, like the init thing, are handled under named actions. And I guess these are possibly like unnamed actions. Where did they go? Down here. And we have some finally action, which is probably some sort of cleanup. Number of alts, maybe alternatives. And whether something is a start rule. I guess we're a rule, right? So we might be a start rule. And we might have alternatives, which is maybe the length of which is maybe a number of alts. And all rules have a unique index. So I guess rules are essentially uniquely named by some index. We have an action index. If lexer 0 to n-1 for n actions in a rule. And then we've got this must be a constructor, right? So the constructor is going to take a grammar, a name, a rule AST, and a number of alternatives. Right? I'm guessing alts is alternatives. And just create this thing. We've also got this other constructor, which how is this different? I guess we give it a lexer mode and Boolean case insensitive. And presumably we tell it that this mode is equal to lexer mode. Yeah. And we set this variable and we populate alternatives by just making a new alternative. We can call define action in alt, which will take an index, I guess, to the current alt and an action AST. And it'll add the action AST and set alt at current alt actions that add action AST. Okay, so this line adds it to actions, and this line adds it to the alt actions, the actions of the alt at the current alt. I don't really know how those are different, but those are somehow different. And then we'll check it for a lexer. And if we are, we're going to define the lexer action. It seems like we're really reusing this action AST thing. Okay. And then we can do a bunch of stuff like define lexer actions, get token refs, get element label names, get element label defs, etc. We can get alt labels, a bunch of getters and setters, resolve to attribute, rule arguments, return values, predefined rule prop. We check if args is null. Attribute A is equal to args.getX. If A is not equal to null, return A. If ret values is non-null, so resolve to attribute, it's going to take a string and a node, which is an action AST. First thing, we're going to check if arguments is null. We check if return values is null. We're going to check if locals is null. And if these are non-null, we're going to create a new attribute out of this stuff. Oh, okay. So I guess we're essentially like looking in args, we're looking in return values, and we're looking in locals. So I guess we're looking at a bunch of different data structures because stuff is spread out in a bunch of places. And we're going to look in this particular order. And the first time we find it, we're going to return it. And if we don't find it one of those things, we're going to call get predefined scope on the rule label. And then we're going to call properties.getX in the predefined scope. And then we have another resolve to attribute, which takes two strings and a node. X is surrounding rule, label ref, and any else. And in this case, we're going to get any label def. I'm not sure what that does. And then you're going to set any label def to that and check if it's null and possibly return some stuff. Okay. All right. I still don't have a sense of what's going on yet. Here's lexergrammar.java. Lexergrammar extends grammar. And the grammar from which this lexicgrammar was derived, if implicit. This is a Java file, right? Okay. We've got some map. I don't know what a multi-map is. From string to rule modes. Maybe you can have multiple rules? No, I don't know. Default mode rules are added first due to grammar syntax order. So we have these constructors which are just calling super. And we've got this define rule thing, which will take in a rule and check if it's defined in the super class. And if it's not defined in the super class, we're going to return false. Otherwise, we're going to check if modes is null. In which case, we're going to set modes to a new multi-map. And then modes, we're going to map the rules mode to the rule. Okay. This is just looking up a rule by its mode. Let's look at what multi-map is. Multi-map. Deprecated. Use multi-valued map. So this seems to be a value of a multi-valued object. We have get, an iterable get, an iterable map. How is this different from a map that returns a set? I don't know. I'm going to just guess it returns some sort of set. I guess it's just got a more convenient interface. And we've got undefined rule, and I guess we just look in the map and see if it's there. Or is it undefined or undefined? Undefined. So it causes the rule to be undefined or to have its definition revoked or whatever. And it just removes it from the map. So here's left recursive rule. So this should be a type of rule, right? So we saw the rule class. Here's an instantiation of the class. We've got rec primary elements, ordered hash map, original AST. Did we delete any labels on direct left recur reps? Points at ID of whatever this is equals ID element. We've got left recursive rule ref labels, new array list pair grammar AST string, left recursive rule. This is just some constructor. Look at whether it has alt specific contexts. We can get the original number of alts. Get primary alts. Return an array that maps predicted alt from primary decision to original alt of rules. For following rule, return 0 to 4. So here's some, I guess, rule. Is this what a rule is? It's like a rule of the grammar. So E, I guess, is either an expression can be a type of expression times an expression, maybe or an int, or a plus or an ID. So 1, 2, 3, 4. The maps predicted alt from primary decision to original alt of rule. For following rule, return 0, 2, or 4. Rather, return the list 0, 2, and 4. I guess 4 comes from there being 4 alternatives. I don't know what 0 or 2 are or how this is predicted. The maps predicted alt 1 to original alt 2 and predicted 2 to alt 4. That maps predicted. I'm not sure. Get primary alts. So get primary alts is going to look in the rec primary alts, see if its size is 0, in which case we return null. Otherwise, we're going to create a list of alts, which are really ints. We're going to get it from the rec primary alt size. Then we're going to iterate over the rec primary alts. And we'll get them. We're just going to get them. And I guess they contain left recursive rule alt infos. And so we're just creating this thing to serve as the target for get. And then we're going to populate alts at I+1 to alt if info alt num. Here's get recursive op alts. I guess more or less the same thing. Here's get alt labels. All right, so let's ask one of these things. Did I close the chats? I think I may have. See if Bard is still around. So in ANTLR, what are alts? And while they're thinking about that, let's just look it up on the internet as well. In ANTLR, alts are alternatives. They are possible ways that a rule can be matched. For example, the following rule has two alts. Okay? So rule E seems to be the result of essentially calling the binary operation on E, or this other binary operation E, or it's an int. This says two alts. Maybe the first one is not an alt, and the other ones are the alternatives. The first alt matches a sequence of two E rules separated by an asterisk. The second alt matches a sequence of two E rules separated by a plus sign. The third alt matches a single INT token. So there are three alts, right? All right. When ANTLR parses a string, it tries to match the string against each rule in the grammar. If the string matches a rule, then ANTLR will choose one of the alts for that rule. The alt that is chosen is the one that best matches the string. Okay? In the example above, if the string is 1 plus 2, then ANTLR will match the rule E and choose the second alt. This is because the string 1 plus 2 matches the sequence of two E rules separated by a plus sign. Alts are a powerful way to define syntax of a language. They allow you to specify the different ways that a rule can be matched. This makes it possible to create grammars that can parse a wide variety of strings. Yeah? There's something about alt prediction, right? Which seems to be different from like just actually matching it. ANTLR predicts alts using a recursive descent parser. This means that ANTLR starts at the top of the grammar and tries to match the input string against each rule in the grammar. It matches the rule, and ANTLR will try to match the input string against each alt for that rule. Okay. So it'll match some rule. I guess this is the rule. So if it matches, I don't know how it knows if it matches any rule. Maybe if it matches any of the alts, checks the other ones, or maybe there's some other meaning of match that we just somehow know is already an expression, and so we look up in this rule. Yeah, okay. So ANTLR uses a number of heuristics to determine which alt is the best match. These heuristics include the length of the alt, okay, the number of tokens that have already been matched, the types of tokens that have already been matched, the context of the parse. Okay. ANTLR also uses a number of optimizations to improve the performance of the parser. These include parsing in a bottom-up fashion, using a predictive parser, and using a backtracking parser. The predictive parser is the most important optimization. This is because it allows ANTLR to predict which alt is the best match without having to try all of the alts. This can significantly improve the performance of the parser. Okay, that's probably part of its magic then. The backtracking parser is used to handle cases where the input string does not match any other rules in the grammar. This can happen if the input string is malformed or if the grammar is incomplete. The backtracking parser allows ANTLR to try different combinations of alts until it finds a match. ANTLR's prediction algorithm is very efficient. Okay, it can handle a wide variety of input strings. However, it's important to note that the prediction algorithm is not perfect. All right, so we need to find the prediction algorithm. That seems to be where the real party is at. Let's see if we can find the word prediction, predicted alt. Now let's look at this thing again. The following rule returns 0 to 4. That maps predicted alt 1, I guess this one, to alt 2, and predicted alt 2 to alt 4. 1, 2, 3, 4, right? Oh, so 2 is mapped to 4. So we're basically skipping 3. Return an array that maps the predicted alt from primary decision to original alt of rule. So what are we passing in? Nothing. We are in a rule. So I guess what we're looking at is rec primary alts. Let's look at rec primary alts. We've got this get original number of alts. We've got get unlabeled alt ASTs. Get primary alts. What is this? Get alt labels. So somehow these are populated, but it's not clear to me yet how they're populated. Is there like a setter? Not sure. Look this up in Emacs. What did I do? All right, let's find rec primary alts. And let's try extract find references. So we've got this recursive rule transformer, which is assigning rec primary alts to some stuff. We've got a left recursive rule, which doesn't seem to be assigning anything. And so the only thing that seems to be assigning to it at all is this rule transformer. Let's look at this recursive rule transformer. Lots of print line debugging. Let's comment it out. To translate left recursive rule, it's going to take a grammar, root AST, which is called AST, a left recursive rule, a string, which is a language. Okay. We've got some previous rule AST, and we've got left recursive rule walker, which will take the previous rule AST, a tool, a rule name, and a language. And we'll try to left recursive rule walk, I suppose. This must be this must have undergone a lot of debugging, judging from the commented out print statements. The left recursive rule walker and get first child with type. Get artificial op prec rule. Maybe this is the thing that prec is different from prediction, right? Or maybe it is prediction. I'm not sure. And then we're going to get the parse artificial rule from rule AST, get child, set child, transform. It's going to be equal to new grammar transform pipeline. Reduce blocks to sets, expand rule collector, basic semantic checks. Then track recursive alt info for code gen. We're going to create rec primary alts as a new array list. And we're going to add all. So the thing that populates these rec primary alts is the left recursive rule walker prefix and other alts. Then we check if it's empty. Prefix and other alts. Let's look at prefix and other alts. Here's the left recursive rule analyzer, which extends the left recursive rule walker. Using a tree walker on the rules determined if a rule is directly left recursive and if it follows our pattern. Okay. So this seems to be the what's it called? Constructor. So the constructor will take a rule AST, a tool, a rule name, and a language. We'll call super new common tree node stream. We'll set a bunch of stuff. And then we'll create a code gen template from the tool. I'm still not sure what a tool is. Let's look at what tool is. Public tool. Did this go to definition? Here's the class. Using tool.java, unsurprisingly. So tool has a version and some grammar extensions stuff, some options, an input directory, output directory, lib directory, generate atn dot. This seems to be like configuration for ANTLR. Gen listener, gen visitor, I guess generate, whether to generate a listener and visitor. A bunch of options. Log manager, listen, and some list of listeners, and a main. That is not indented. Can you do this? Maybe not. Where did main go? I don't know why I didn't find main before, but this seems to be main. Shouldn't there be a way to format? No. So I can set the style and then indent line or region. All right, that seems to have worked. Okay, so here's main. All right. So we'll check the arguments, make sure that, I guess, we have non-zero arguments. Oh, hey, I missed a chat here. Hey, Nassim. Aren't you skimming over the source? Isn't there a better approach possible? Possibly. If you have a suggestion for a better approach, I'd be curious to hear. So here's process. So the main thing we do is we try to call process grammars on command line, and then finally we just log some stuff, and that's really all we do. So that's what main does. So process. Let's take a look at. How do we not have that? So oh, you know what? Maybe now that I formatted, do I have to regenerate tags? That'd be a tragedy. What I meant to do? Oh, it's because I'm in God mode. Let's try that again. Tool.java. Well, that's not a real file. That's why. I think yeah, let's try this again. What is my shell? Okay, so that regenerated. Let's see if I can. Okay, still not finding. Let's just try grep. Oh, it's just in the same file. The process grammar is on command line. I'm going to call sort grammar by token vocab on the grammar files. Sort grammar by token vocab. And then we're going to iterate over the grammar root ASTs of the sorted grammars. And we're going to call create grammar on T. And then we'll set g.filename to the t.filename. And if we're supposed to gen dependencies, we'll call the build dependency, we'll get the build dependency generator from the G file, from the grammar. And else if some other stuff. And then, okay. And if we have no errors, we'll call process on G with true. And what if we need to process with false? I'm not sure what happens here. If gen dependencies, we'll get dep, and then we'll call print line on get dependencies render. Otherwise, I'm not sure what this is. This seems to just be something that like logs and exits. But it seems like process G true is the thing that actually has this stuff. It says to process a grammar, we load all of its imported grammars into subordinate grammar objects. Then we merge the imported rules into the root grammar. The root grammar is a combined grammar. We have to extract the implicit lexer. Okay. Once this is done, we process the lexer first if present, and then the parser grammar. So process, we're going to load grammars. Get a new grammar transform pipeline on this, and then essentially declare some variables. We'll look at the GAST. If it's null, and if its grammar type is ANTLR parser combined, and G has errors, then we'll extract the implicit parser, which is just some method that I'll black box. And if the lexer AST is non-null, and the grammar options is non-null, or rather, whatever, I'll ignore the grammar option stuff. Then we'll get a new lexer grammar from the lexer AST, set some file names, set the original grammar and some other stuff, and we'll process the non-combined grammar. And if we're down here, we'll set implicit lexer to null. Sorry, no. If implicit lexer is non-null, we'll import the vocab and process non-combined grammar down here. And then process non-combined grammar is going to, I guess, continue the parsing operation. It'll check if the AST is null, if it has errors. We'll check rule for issues. Rule, I guess some sort of sanity checker. And we'll create a semantic pipeline. Make sure grammar is semantically correct. Fill in grammar object. And then we'll process the semantic stuff. An error on return. Then we'll call code generator create. And if that fails, we'll return. And here it says build ATN from AST. So we're going to build an automaton with an automaton factory. And if we're a lexer, then we're going to set it to the lexer automaton factory. Otherwise, we're going to get a parser automaton factory. And we'll set G automaton to whatever we got from whatever we get from the factory. We might need to generate dot files, which is for GraphViz. And if we need to generate code and that we have no errors, then we'll create this generate interpreter data thing, some interpret file, I guess, and try to write it. And we've got this analysis pipeline, and we might call anal process, and we'll look for errors, and then we'll call gen process, which should generate the actual code. All right, and so a Java project. What? Do people hate Java? I actually think Java is not as bad as people think. I had to work in Java, and going in, I was reluctant to do so, but I actually kind of like it. One thing I do find with Java though is that some of the stylistically, it's kind of this I associate it with object-oriented programming, but it's kind of the style where like you have to really dig to find an implementation. There's so much kind of overhead. around setting up class structures and getters and setters. And that kind of verbosity makes it so that like you really have to hunt for where the real work is being done. So Naeem, to answer your question, I wanted to look through that while it was in my working memory. But to answer your question, isn't there a better approach? I don't think that there is a better approach. So what we're doing in this show, this is always code that we're unfamiliar with, and so I think the optimal approach is to do some sort of like skimming, strategic skimming on the first pass, and there's just too much information. The first thing you need to do is kind of find out what you don't know. And the quickest way to find out what you don't know is typically to do something like skimming, or something that I think is fundamentally going to be equivalent to skimming, even if you call it something else. So so that, I mean, but that's an empirical claim. So I'm happy to hear if there's evidence to the contrary. People have suggested all sorts of other approaches, and so far, what people have suggested have been approaches that I've tried before, and I find that they don't really work at scale. They might work for a small project, or they might work if you have a lot of context. And but yeah, that's my approach. Basically, some form of iterative deepening breadth first search. But because we're covering so many new projects, for the most part, it's been a new project each time because I'm trying to work through some of these recommendations from fans. We only get like the first pass, but for some of the other stuff, we're gonna, as we do more passes, we dig deeper and deeper into the code. But it is true that in this case, it's taken me a while to find out where the code that actually does stuff is, and really, it took me a while to find out what even needed to be done, and like how the thing was structured. So I mean, that wasn't optimal, but it kind of depends on the project, how the project is laid out, how legible they want to make that sort of structure. And to return to Abhishek's point, I think Java tends to obscure that structure a little bit, just because of not because of the language itself, but because it's so historically caught up in a really kind of like fundamentalist, object-oriented approach that who was it, Sun was promoting at the time. Okay, so this is main, and so there's a sensible structure here now, and that structure is process everything in turn. So first, get the grammar, create a lexer, create a parser. There was some other step somewhere, but then like generate code basically, and along the way check for errors. So I think all of that's straightforward-ish. I still don't have a sense of what this AST stuff is. Let's see if we can find the lexer. Build. Okay, so we created an automaton, and the automaton is, I'm going to think of basically as as regular expressions for parsing things. Process non-combined grammar. I don't know what this stuff about combining is. I guess if you have two grammars, you have some way of combining them, maybe concatenating them to like so that one is a subgrammar of another. I don't know what sorting the grammars means. Look at sort. Hmm. You just sort grammar by token vocab. Get a new a graph of strings and a grammar root AST. So the AST thing should be some tree essentially of some kind of nodes. I guess grammar nodes. We're going to read in the grammar, and that grammar should give us some sort of AST. Let's pull up a where's my, there we go. Let's pull up an image of an AST. It might look like this. But I think what it might mean is really the syntax tree, which is different from an abstract syntax tree, right? A concrete syntax tree. Different from a parse tree for sure. The parse tree is an ordered rooted tree that represents the syntactic structure of the string according to the context-free grammar. It's used primarily in computational linguistics. Oh, okay. Well, maybe they don't use this in computer science. So here's a like classic AST. So we've got some statement. I guess this is the root. You might have like a while statement, which has some comparative operator and some variables. In the body, and there I guess branch is probably if, etc. And you get a tree. That's the sort of thing that we should get. Whatever. That's the sort of thing that root AST is, I would guess. We're going to iterate over file names. We're going to parse the grammar and get a grammar AST back. We already had a grammar root AST. I don't know how those are different, other than that one, I guess, is a root or has a root. And we're casting. What are we doing here? We're taking T, which we got back from parse grammar. Okay, so roots is, I see. So we're maybe in a forest. So we've got some list of roots. And here, okay, so we're going to iterate over, yeah, okay. So we're going to iterate over files and get the particular roots. And probably we're going to add them to roots, right? Roots.add, here we go. Okay, yeah, so I think we're in a forest, which has possibly multiple rooted trees, maybe one for each file. Whatever token vocab node is, so I guess we're going to figure out what the vocabulary is. Most grammars depend on any, make grammars depend on any token vocab options. Find option value AST. I'm not sure where that's going to be. We check the token vocab node is false. Maybe we'll look at this. I don't know why etags is not working. Let's try just closing Emacs. Let's try not only closing Emacs, but also just deleting the tags file. We'll just declare tags bankruptcy. And try again. And let's look at root abstract syntax tree. Okay, so grammar root AST extends grammar root AST with options. Okay, and we've got some default options and a token stream. So the root abstract syntax tree, which has options by virtue of extending this thing with options. It seems like with options should extend grammar root AST, doesn't it? It's more specific. But anyway, the root AST has a token stream. So those are all the tokens, I guess, that we read. We've got some command line options in a file. And when we create one, we're going to give it a grammar type. No. Wait, what? we can create one from a node. This is kind of like a copy, maybe a copy constructor. What we really want to do is create one from a token. We'll give it a token and a token stream. We'll call super on the token. Check that the token stream is null. Otherwise, we just set this token stream to token stream. But what do we do with T? I guess we called super on it. Let's see what super does. Super will be, I guess tags can't find super. Okay. Grammar AST with options has a node and extends grammar AST. Okay, I guess root grammar AST extends grammar AST with options, which ultimately extends grammar AST. Okay. So we still, yeah. All right. So at any rate, when you have with options, you're a grammar AST in particular. So you have a node, but you've also got some options. So this is one of the things like, one of the things people are into is composition over inheritance. So this seems like this could be just composition. Instead of having a subclass that just has this extra options thing, we could have just be able to compose a struct that has an AST and an options. And that way we wouldn't have to have this deep inheritance. So here's grammar AST, which again extends commentary. Let's see how far this goes. Oops. No definition found for common tree. Well, it's a runtime tree. Okay. So common tree, I guess, is the common tree. And a grammar AST has a grammar. That's good. An ATN state, which is the state of the automaton. I don't know if we have an ATN yet or just the state. And a string text override, I don't know what that does. And you can create a grammar AST from a token, which just calls super and common tree. All right, so let's find common tree. Before maybe runtime. What? Where do we think this is? Oops. So common token stream. Let's see. That's common token stream. No, I don't want common token. I want, what was it? Common tree? All right. We have some stuff in semantics, some stuff in, we have this import. I don't know where this is. Maybe it's in another repo. Okay, well, let's ignore that then. At any rate, so we can create a grammar AST from a node, which is just copying stuff. And we can get this common token stuff. Get nodes with type preorder DFS. Yeah, I find this code a little bit hard to decipher. Not because necessarily of its complexity, but because I don't think I understand the style yet. Get first descendant with type. Get first descendant with type. So you can pass in some type, I guess, and you'll look over the children until you find one. You'll walk the tree, I guess, until you find one with that type. You can set type on a token. So is this a tree or a token? Do we just have one token? Where are our class members? I guess token is maybe part of the common tree, public interface token. A token has properties, text, type, line, character, position in the line, so we can ignore tabs, token, channel, index, and source from which we obtain this token. So, okay, so I guess it does have, yeah. I guess in the abstract syntax tree, like this, the token is the label of the node, maybe. So that's, so, but maybe this is really a node and not a tree. Here's children. We can get the children. Parser rule context, extends rule context. If we are debugging or building a parse tree for a visitor, we need to check all the tokens and rule invocations associated with this rule's context. This is empty for parsing without tree constructor operation because we don't need to track the details about how we parse this rule. So we've got some children, which will return a parse tree. But we are not a parse tree. We are a rule context. Okay. And we've got token. We've got start tokens and stop tokens for debugging and tracing purposes. Parser rule context. Org ANTLR runtime tree. Let's just try looking this up on the internet. Common tree. Maybe it's in the ANTLR 3 repository. A tree node. Okay, so it's not a tree, it's a node. Which, recursively you can get the, yes, the tree, the node probably points to other nodes. And in that sense, it's the root of a tree. A tree node is a wrapper for a token object. After 3.0 release, while building the tree rewrite stuff, it became clear that computing parent and child index is very difficult and cumbersome. Better to spend the space in every tree node. If you don't want these extra fields, it's easy to cut them out in your own base tree subclass. Okay. And so this is some Java doc thing. We've got child index, parent, start index. And we can create one from a token, create one from another common tree. Whatever dop node is, maybe duplicate node, get line, get token, is nil, set child index, set parent to string. Okay. So basically a node, a classic node of a tree. All right. And so grammar AST is in particular a node of a tree, but it also has a grammar. Let's look at grammar. I think we looked at maybe grammar before. Grammar.java. Yeah, I think we did look at this. We've got, so the grammar has parser options and lexer options. And we've got this grammar root AST thing, which has a token stream. Track token stream used to create this grammar. We transform grammar, track original unaltered token stream. So we might transform the grammar, I guess, which will change the token stream, and then we keep a like a reference to the original token stream. We've got some test-only stuff. We've got a file name. We might have an implicit lexer. I don't know what makes it implicit. If we are imported, who imported us? If null implies grammar is root. And then we have also imported grammars. Maybe this is for like when you're parsing something, like there's an actual literal import statement. And this is keeping track of that. We've got some ordered hash map, and the grammar has the automaton. So where we have is lexer. The grammar can be a lexer. We have is parser. Oh, I see. Oh, okay. So combine means it's a combined parser and lexer. So traditionally, if I understand correctly, you lex first, and then you parse after your lexing pass. But and that's done for a variety of reasons, I think. But maybe one of which is that it makes it easier to think about what you're doing. And then, But alternately, you can lex as you parse. And I think that's what it means by combined. And that's probably more efficient, but maybe also harder to manage. Could it just, yes, that's right. Could it be a tree as an entry point root node? Yeah, it will. It roots a subtree. That's right. It's a yeah. So it's a tree in the sense that it's like, I guess what I'm thinking is that at least in an object-oriented approach, like conceptually, the things that are like attributes of a node are a little bit different from the attributes and behaviors of a tree. So if you have something like a class called tree, that kind of, I would expect there to be like tree methods, like walk down all of its descendants. But if you have a class called node, I would expect that to contain things like uh, uh, labels or attributes or token. And so it's a little bit weird to me to see a class called tree and then have something like token associated with it, because token seems like token conceptually is associated with a node. And so it's just, I guess it's really just a confusion I had about the variable naming convention or the class naming convention. But yes, you're right. It roots every node roots a subtree. It's just the classic recursive definition of a tree or a graph or something. Okay, so I think that's what combined is. I think it's a combined lexer parser. And I'm beginning to get a feel for how the code is organized. And so code gen, I'm going to ignore. I think what I said I wanted this to be about an hour. See if we can get it about 2 hours, I guess. In my remaining time, what I really want to see is the prediction stuff, if I can find it. Let's just try grep. Case insensitive. Ready? Oops. Keep thinking that will do something other than close the grep window. Okay, so we have predicate, which is not what I want. So sempred is probably, that's predicate. What about predict? Time in prediction, decision info, interpreter. Prediction mode. So we can go to prediction mode. Okay, here's prediction mode. Where are we? ANTLR runtime. Here's runtime. Okay, all right. Okay, prediction mode. This enum defines the prediction modes available in ANTLR 4, along with utility methods for analyzing configuration sets for conflicts and or ambiguities. Prediction mode. The SLL star prediction mode. This prediction mode ignores the current parser context when making predictions. Okay. This is the fastest prediction mode and provides correct results for many grammars. This prediction mode is more powerful than the prediction mode provided by ANTLR 3, but may result in syntax errors for grammar and input combinations which are not SLL. Okay. I don't know how it works. Like, does it verify its prediction? Or does it just error out? When using this prediction mode, the parser will either return a correct parse tree that is the same parse tree that would have been returned with LL prediction mode, or it will report a syntax error. If a syntax error is encountered when using the SLL prediction mode, it may be due to either an actual syntax error in the input or indicate that the particular combination of grammar and input requires a more powerful LL prediction abilities to complete successfully. This prediction mode does not provide any guarantees for prediction behavior for syntactically incorrect inputs. Okay, so I guess if you call this and you get a syntax error, then you have to essentially call again with LL because it will give you false negatives. So this is just an enum. So this is just literally the SLL thing. Then we have LL prediction mode. This prediction mode allows the current parser context to be used for resolving SLL conflicts that occur during prediction. Okay, so now we're going to take into account the parser context, whereas before we didn't. This is the fastest prediction mode that guarantees correct parse results for all combinations of grammars and syntactically correct inputs. Very cool. When using this prediction mode, the parser will make correct decisions for all syntactically correct grammar and input combinations. However, in cases where the grammar is truly ambiguous, this prediction mode might not report a precise answer, exactly which alternatives are ambiguous, or which alternatives are ambiguous. Okay, so your grammar might not be right. It might have some ambiguities, but if you use this mode, I guess it'll detect that it's ambiguous, but it won't give you a great error message maybe that tells you exactly where the ambiguity is. This prediction mode does not provide any guarantees for prediction behavior for syntactically incorrect nodes. Okay. And then we have LL star. Wait, no, this was LL star. Okay, so this next one is called LL exact ambig detection. This is, I guess, LL star with exact ambiguity detection. Cool. We have some map called alt and context map that uses just the state and the stack context as the key. And some equality operator thing. Here's the SSL implementation, it looks like. Computes the SLL, not SSL. Computes the SLL prediction termination condition. The method computes the SLL prediction termination condition for both of the following cases: the usual SLL plus LL fallback upon SLL conflict. Okay, so maybe I said that you would have to call LL if you get an error, but it seems like maybe they have some way, some method you can call which will fall back automatically in case SLL fails. And then we have pure SLL with LL fallback. Whoops. Oh, I just did. And so when it's fallback is enabled, correct predictions are ensured regardless of how the termination condition is computed by this method. Due to the substantially higher cost of LL prediction, the prediction should only fall back to LL when the additional look-ahead cannot lead to unique SLL prediction. Okay, so we'll ignore the rest of that. So here's heuristic. As a heuristic, we stop prediction when we see any conflicting subset unless we see a state that only has one alternative associated with it. If there's a conflict, we stop unless there's a state with only one alternative. The single alt state thing lets prediction continue upon rules like this thing, I guess. Otherwise, it would admit defeat too soon. So this is some code snippet, which we ignore the documentation markup. Seems like it has alternative 12 goes to 1, which goes to the empty list. And then 6 goes to 2, which goes to the empty list. And then 12 goes to 2, which goes to the empty list. And then S is either an ID or an ID and an optional ID with a semicolon. I don't know what that means. When the ATN simulation reaches the state before the semicolon, it has a DFA state that looks like this thing. Basically this part. Naturally, 12.1 and 12.2 conflict. Oh, okay. So 12.1 and 12.2 do conflict. Yeah, that makes sense. But we cannot stop processing this node because alternative 2, maybe 2.0, like this, alternative 2, has another way to continue via code 6.2. Okay. So if these conflict, has one alternative associated. So if these conflict, I guess we choose 6, 2. Also, let's us continue for this rule. 1, 1, 0. Okay, 1, 2, 8, 3. And then A is either of type A, big A, or type big A, or type AB. I don't know how these differ. After matching input A, we reach the stop state for rule A, state 1. State 8 is the state right before B. Clearly, alternatives 1 and 2 conflict. 1 goes to 1 and 1 goes to 2 conflict, because you don't know whether to go to 1 or 2, I guess. And no amount of further local head will separate the two. Okay, so is this 1 goes, maybe 1 goes to 1 means this goes to this, and 1 goes to 2 means this goes to this. The other option is, what, 8 goes to 3? I don't know what 8 is. 1, 2, 3, 4, 5, 6, I don't know. In the previous example, we're concerned with the states associated with the conflicting alternatives. Here, alt 3 is not associated with the conflicting configs, but since we can continue looking for input reasonably, don't declare this state done. And here's pure SLL parsing. To handle pure SLL parsing, all we have to do is make sure that we combine stack contexts for configurations that differ only by semantic predicate. Okay, I'm not going to read the rest of this. I'm not really sure that I follow. I think that I would need to know more about the literature on parsers in order to know really what they're saying. But we have this has SLL conflict terminating prediction. So this is going to do the thing that I just said in the comment. If prediction mode is SLL, don't bother with combining configs from different semantic contexts, etc. So we'll get conflicting alt subsets and apply some heuristic and maybe return that heuristic. Boolean heuristic. I guess heuristic is whether to keep going. And the heuristic has conflicting alt sets and does not have state associated with one alt. Okay, so if it has states associated with one alt, then this would be true. But has conflicting alt substate would also be true, so we would return true. Otherwise, if we have just the first thing but not the second, I guess we would be false. All right. And then we have has config and rule stop state and more heuristics. Okay, so I'm not going to go deeper into this prediction stuff because it's clear to me at least that that either one of two things would need to happen. Either I would need to know more about like dig deeper into the grammars, or just know more, have more context in general around around the world of grammars and parsers and lecture, like the research literature. I don't have either of those, but this is, in my opinion, if you were really into ANTLR 4, this would be a file that I would really try to understand. I'm just curious what the ATN state has. Okay, we have some constants, including invalid type, basic, rule start, token start, rule stop. And these can be serialized as strings. Then we have state number. Are these state numbers? These are constants. Following images show the relation of states for various grammar constructs. Seems like if they're going to be images in the Java doc, I guess let's look at that. Okay, so we get some sort of picture. So rule start state has some I guess goes to content and then rule stop state. So that's a rule. Block of one or more alternatives. Begin, block, basic block start state. You have different alts, and then a block end state. And I guess each alt is a rule. And then we have greedy loops, which has a start loop entry state with some alts. If you're in alt 2, you go to the loop end state. If you're in alt 1, you have some start block, just like this one, with alts. And you go to block end state, and then you go back to the loop. And then greedy positive closure. Whatever plus block start state is. And then some alts, block end state, back to the loop. And then somehow you get to the loop end state over here if you get the plus loop back state in alt 2. Oh, okay, so plus is here. So star should be any or more. Or 0. Assuming this is like the regular language stuff, this should be 0 or more, which I guess is why alt 2 means maybe there is 0, we just end. And then here, plus should be at least 1 or more, so we should flow through this at least once, and then maybe there are no more and we end. We have this notion of epsilon terminations. The following images show the relations of states and transitions. Solid edges marked with an epsilon indicate epsilon transition. Dashed edges indicate locations with where any transition is derived from transition might appear, and so on. I'm not going to read the rest of that. Okay, so this is also something that's worth looking at. So this is now I think this is making the logic of the overall project make sense more. And we've seen, I saw classes for, or at least the names of files that had like things like the block state. And so this should all be modeled in the Java. But I think I'm going to end it there just because I'm running out of time. But that was actually more interesting than I thought it might be at first. I thought it was going to look a lot like other compiler and lexer, parser sort of stuff. And we get some of that, but it seems like the real thing that makes ANTLR interesting is probably this prediction stuff. And that is, we really only kind of came upon that at the end because we had to spend a bunch of time trying to figure out how things were just wired together and finding out where the right entry point was. So, but that was cool. I mean, hopefully if you use ANTLR, there's enough there to at least get you started exploring more of how it's implemented. And I know there are ANTLR books. I have some book for ANTLR, probably ANTLR 3, and maybe at some point I'll come back. Maybe I'll read that book and come back. And I think just thematically, we're going to continue to look at various things that might be related to compilers and programming languages and programming language design and that sort of stuff. So, so this was really interesting. I forget the name of the user who suggested this. Maybe I can find it. Let me find it. But this is one of the earliest recommendations. Here, ANTLR 4. Hate is expectation. All right, so hate is expectation. Thanks so much for this recommendation. Sorry it took me a while to get to it, but that was cool. And hopefully there was something in that was useful to you. And at any rate, like I said at the beginning, the next 4 weeks will be a little bit different because I'm having visitors, and that limits to some extent my access to where I film these things. But I will still be around, just not. But at least for this week, we're not going to do a roulette. Next week we should be able to resume roulette, and then my goal is to be able to pop in and do probably mostly coding rather than code reading in the next week possibly the next few weeks. But the schedule will be a little bit less predictable. And I will be around. I am upping my social media game, including the Discord server, and I'll try to hang out on Twitter a little bit. We'll see how that goes. So thanks for watching, and see you again soon. Oh, and hi, Sinnerman. That's a good name. Unfortunately, I think you just caught me as I was signing off. But it's good to see folks in the chat. I really appreciate it, and I appreciate the comments and the subscribes. Thanks a lot to everyone. All right, that's all.